Normal distribution. I apologize for not getting this out a little bit sooner. I've recorded this thing about 5 times just because this is a great lesson to teach in class, but it's a little bit difficult sometimes to explain online. So I'm going to try my best, and I'm going to break this up into 2 parts. So this particular video is about the beginning part of the section, which explains kind of the underlying theoretical idea of normal distribution. And the next video is more attacking those practice problems and give you some examples. So what I'm going to do here is I'm going to dive in. If you guys recall our dice experiment thing, I'm going to get rid of the distribution. So what I want you guys to understand that normal distribution deals with continuous variables, not discrete variables. So in our sections up to this point, we've kind of looked at, say for example, how many pizzas were sold, or how many brothers and sisters you have, things like that, things that are discrete. Now when we talk about continuous variables, which is like height and miles per hour you drive to school and things like that, where if you recall we can get down to the exact and like really kind of there's no ending to how far we can break that down. For example, like weight, I could say I am 200 pounds and something ounces, and then something ounces, and then kind of get as exact as I want to get. So that's where we're going to dive into continuous variables. So to show this example, I just want you to pretend like we are getting people's heights in the building. So let's say, for example, I survey 10 people, and these are my heights. Don't pay attention to the dice. I'm just using this as an example. And let's say I survey another 10 people, another 10 people, another 10 people. You'll notice that it starts to kind of mimic what we would call a bell-shaped curve, all right? So the more people I survey, let's say if I'm doing height, the more people I survey, the more and more and more it's going to kind of mimic that bell-shaped curve. So you'll notice I'm just doing a continuous one now. You'll notice that as I survey more people, it's eventually going to end up with that bell-shaped curve. All right. Now let's talk about continuous variables. So let's say, for example, instead of just doing 2 dice, I do this, and you'll notice that it gets more and more related to a bell-shaped curve, similar to what you would see with a height. We have really tall people, we have some short people, and we have a lot of people that fall right in the middle of our population. Okay, and that will adjust depending on kind of the population you're looking at. So the idea of the normal distribution deals with continuous variables. So I'm going to put this away just for like a little bit, the dice idea, and I want to bring up our slides here. So what we have here is, again, we're talking about approximately normal distribution. So if you recall, like the dice thing, we know that if I roll a dice 10 times, I might get different numbers. It's not going to be exact. For example, I should, if I roll the dice 6 times, I should theoretically get 1 of each number because everything has 1 in 6 chance. But as we proved in class, that's not possible. So we can assume that such as heights, they're approximately normally distributed if I were to survey a bunch of people. But also we have something called the theoretical curve, or something you've probably heard of is the bell-shaped curve, assuming that if we were to survey infinitely many people, it would get more and more into that theoretical curve or the bell-shaped curve. And if you guys recall that little thing I flipped down with the little beads, that's kind of the Gaussian distribution as well. Okay. So let's talk about that equation. So here is the amazing equation for a mathematical equation for a normal distribution. So you can notice that the u here, or mean u, is the mean, and we have our standard deviation implemented in there. This x value is the variable there. And so let me show you guys just how this can get really bonkers if we really want to, but it's not really going to get that bad because we're going to do a standard normal distribution. But I digress. Let me get to this part. So for example, here's the equation. I did this up on Desmos. And so you'll notice here is an equation of a bell-shaped curve. I just typed this function into there. And then if you notice, if I change the standard deviation, you'll notice that the bell-shaped or the curve changes. And that's just because I'm plugging it into this function. Also the mean, if I were to switch around the mean, you'll notice that it goes back and forth from side to side. So the standard deviation will kind of level out the bell-shaped curve if it's a high standard deviation. And if you recall on this that if, let's say, for example, the mean were, let's put it at 0 so I can show this, and you notice that, all right, so if I'm talking about the mean is, or the standard deviation is smaller, that means that 1 standard deviation out would have these areas here. So if we were to have, like, every data set has different means and standard deviations. So you can imagine we'd have infinitely many different bell-shaped curves if we don't take this one step to make it into a standard normal distribution. Okay, so this is probably the last time you'll see this equation, unless you're taking stats in, well, I'll bring it up once in a while, but we're not going to use this, okay? So you're not going to have to plug numbers into this, okay? So some of you calc students will see how this applies to calculus, and that's what I'm going to talk about here in just a second. So this idea right here from the slides is what I just talked about, how if we change the curve at standard deviation, it flattens out. If the standard deviation is higher, if I make the standard deviation lower, it really peaks up. All right, and also if I change the mean, it goes back and forth. Now in section 6.2, we actually apply this to application problems, so it would probably make more realistic sense then. But I am just showing you that the mean. What I'm trying to show you here is that we can have infinitely many different normal distributions based upon the standard deviation and the mean of our data. Okay, so let's eliminate that a little bit. Okay, there is one thing I do want to talk about, is that if you recall this nice thing, the normal distribution properties, is that I just want to talk about this. The total area underneath the normal distribution is 1. So like see this area, pay no attention to this blue that's coming down off of 0, just this piece right here. So the total area underneath this curve, calculus students, is 1. And so what we would do here is the standard normal distribution allows us to, instead of having to take the integral of this and then finding the area underneath the curve, which would be an insane amount of work, right? And of course, you calc students know that. Instead of having to do that, I'm going to do what we call a standard normal distribution. Okay, so I'm going to make the mean 0 and standard deviation 1. And that will make this equation a heck of a lot easier. You can understand that instead of having this, I'm just going to use what we call the z-score, which should be familiar. We've used this before. All right, so so instead of having all these different distributions, I'm going to have a standard deviation of 1 and a mean of 0. Okay. All right. So I'm going to be using the standard, the z-score, to find that area under a curve. Again, the probability, the area underneath a bell-shaped curve is 1. Again, I rephrase that, area under a curve. So if I wanted to find the area under this curve, in particular, I would have to find the integral of this, and then depending on what I'm asking for, I would have to find the area of that segment. Okay, but we're not going to have to do that. So you don't have to know calculus to know how to find the probability. So what we're going to do is essentially take any kind of data that we have. Let's say I have this different mean and standard deviation. I'm just going to essentially make this mean to be 0, and then I'm going to use the standard deviation to be 1. 1 out, and then another 1 if I wanted to, 2, and then negative 2. So I'm going to use, so I'm going to plug in 0 and 1 in this equation, all right? And so that would make it a lot easier, okay? And you're probably asking, well, how can you just do that on a whim? And the reason I can do that is because I use the z-score, which incorporates each individual mean and standard deviation of the data. So essentially what I'm doing is I am changing the graph to be more in my favor so that I can find a universal normal distribution. Okay, so what you'll notice in your practice problems here is it's going to ask you for find the area under the standard normal distribution curve to the right of z equals 2.11. So what it's asking for is what's the area of this space 2.11. So we would have to find that. Now, so in the next video, that's where I'm going to go through some of these example problems from your practice. This video hopefully gives you a general idea of how standard normal distribution works. If you are still a little bit confused, which I can understand because I love teaching this lesson in the classroom, I have those office hours that I would love to kind of break this down more if you still have questions about it. So or you can email me with your questions. So the next video, we're just going to go over the practice problems more in depth. Thank you.